Okay, so hello everyone. Welcome to the first installment of the Comprehensible Seminar for 2021. So we have a special talk in two parts now by Kiao Peng, so this week and next week. And for the first time, we're both live at the lab and on Zoom. So people on Zoom, don't hesitate to ask questions in the chat and I'll read them out during the talk. And people in the room can ask as well, of course. So yeah, without further ado, Kiao.
Thanks. It's a great honor to give the first talk of this year and in this upgraded salon talk. So my topic today is the homotopy type. And for this part, I will focus on why there is a homotopy. So it's not so much type theory, but next part we will dig into the type theory and the logic. So in first place, so why a mathematician should care about homotopy type, or for short, we just call it type. So our math was based on sets. But set is something, maybe some abstraction of collection. So it's kind of multiple things, but it's kind of discrete. It's kind of some set. So if we want to group it together, it will become space. So space will have more information that's it. So we want to find the abstraction for space. So here, what we get is the type for homotopy type. So what we want to do is to replace the notion of set into the type. But the first question is, why do we want to use space to interpret our math? So let's recall some notion of homotopy theory. What is a homotopy? So assume that f and g is two continuous maps between x and y. And so a homotopy is something. All right, so this is a 0 to 1 y, such that right, this is very elementary notion. But if we want to change the point of view of this, so if we fix the I, it will become if we use I as a variable, so it will become I put in a I and then we convert a function or map between x and y. So if x and y it's a reasonable, it's good enough, we may have some space structure between the continuous map from x to y. So this is space. And so what's the homotopy? It's kind of like a path between this point. This space is map x to y. So homotopy in fact is just a path between two functions or two maps. So why this notation will bring us benefits? So let's try to find out some. For example, we use this to denote the homotopy class. Or map. So this is easily defined by I0 of this map. Right. Since the path it just
sorry, I think there's a problem with the camera. Just for a second, give me a second because I think it's
okay.
The camera's gone. So
all right.
Okay, it's back. Sorry.
All right.
I'll just zoom back a bit and it's good.
So
Okay, we're good. Sorry.
We continue. So we just represented that. So this is the homotopy class of the map between x and y. But this is just the pi zero. It's take the connection component of this map space. So since this part is just the homotopy. And then we can define so-called the path space. So Px, y. It's just the path with given endpoints. Right. So if we, so this is also it's a subspace of this space. So this we can also compute its pi zero. So what's the pi zero of pi x with 2 points in x? So it's just what we're familiar with is the fundamental group. And if we firm, this is also a path. So if we consider this path space, it's a path space of a path space. So our basic space is this path space, and we take 2 points. These 2 points identity paths at x. So what's the path between these two? If we take the pi zero, what will be? So it's very interesting is that imagine there is a sphere, and so there is point x, and if we draw a path, so our path, so this is begin with identity x, then we move along with this sphere. Then we back to identity x. So this movement between paths is exactly move into a sphere. So this is what we were familiar with is pi 2. It's the second homotopy group. So we can define homotopy group in this very concrete, not concrete, in this elegant way. We do not define what sphere is, or so this may give you some hint that if we use this notion of space as the basic elements, so it will become very convenient. So now, what's the data, or what's the information we want to catch in a space, or to abstract the space? So we have many notions like topologic space, but since topologic space is not good enough, so we want to use another notion. So I will introduce so-called infinity group point. So I will explain what it is. So let's begin with one group point, or just group point. Normally we call it group point. Group point it's just a category. It's all morphism. Isomorphism. So it's kind of very simple category. So let's give you some example. To give a group G, we can define a group point called BG, which object only have one point, and it's morphism between this it's just the G. So you can imagine that there's points and all the morphism is just G belongs to G. So we can compose two morphisms, but it's the since this group, so everything can invert. So there is a group point. So what the group point do with the space? So we can define such kind of group point called the fundamental group point of pi1 over space X. So its object points belongs to X. Then its morphism between X and Y is exactly the pi zero of so I need to remind you that a category is something the morphism is exactly the set, is a set. So we need to take the pi zero to make this become a set. This will be a group point. So this also you can interpret it as the homotopy path of the path between X and Y. So this notation, what this notation can bring to us is that, so for example, is that like if we take we will again get the fundamental group. So there is a very famous theory called monodromy theory. It says that the covering, if X is good enough, covering that means that all the morphism above X is a covering space. So this category is isomorphism to the functor between I1 X to set. So this is the set category. There may be some version you may be more familiar with is that it's also the category of the type 1 XX set. So a set with this pi 1 action on this. So they are basically the same thing. So this may help you that okay, something above X over X can classify like something like group point to set. But this is not enough since we can only classify the covering space. So it's kind of fiber, it's just a set. If you want to classify more complex fiber like a vector bundle, so we will find this is not enough. So what we do is we can keep going on. Yes, we can define so-called two group points. A two group point is very familiar to group point, but its morphism are one group point. So it's kind of the enriched category. Its morphism are not just a set, but its morphism are a group point, one group point. And somehow it's invertible. We will not define the invert notion here, but we will give you the definition. Also, we can get from a space, we can define the pi 2. So again, its objects are points in X, and its morphism. Now we want to the morphism become a groupoid. So fine, we just define a groupoid. It's a groupoid of path space between X and Y. So imagine that this is kind of like there is space and the point is object, but we also catch the information of the homotopy between two paths. So we need to encode this in this morphism. So this I remind you, this is a groupoid. So as you can see, we can still define the n groupoid that its morphism is n-1 groupoid. So why don't we just directly define so-called infinity groupoid? Infinity groupoid is something more morphisms are again infinity groupoid. So infinity minus 1 is again infinity. So we can define the high infinity of space X again this point in X, the morphism. So now morphism should be an infinity groupoid. So I, the morphism is I infinity. Or maybe there's kind of secret argument that we define infinity groupoid by infinity groupoid. But it's fine. Okay, so this is an example of an infinite groupoid. So you may convince that so many homotopy information of this space was captured by this high infinity.
How do you define this by infinity of the vector space, for example?
So
like
okay,
a limit or something?
let's choose some example. Right. So maybe there is a contractable or a point, because we are talking about homotopy. So point it's exactly a homotopy to a homotopy isomorphism equivalent to contractable. So what is a groupoid, infinite groupoid? So we call it state. The state has only one object, and so its morphism it's again state. So all of this was only one point you can imagine. So we can define its morphism is just identity, and the identity between the identity is only identity. So all of this path is only one point, or contractable space. Maybe the second example is empty space. The empty is very easy to imagine. So it's empty. So, like if we want to define a set, the set can be regarded as a discrete space. So maybe we can somehow to define a because setoid, a setoid maybe A. So A maybe its object is some sets. Maybe we will again use, so there is some sets, maybe we add some 0. And it's morphism of xy. It's something sick or empty if x equal to y. So you can imagine it's exactly discrete. So if there only have the path between to itself. So this you can is a space of one point. But so all this was constructed based on set theory. So this is not the correct notion of define. So homotopy type is basically the same thing as infinity group point, but it's not defined in that way. So like here we define an infinity group point by dig into this thing inside, and we describe what the morphism is. But type is kind of like we work it's external. We define a space by its universal property of this. So let's okay, I want to take this. This we will do this later. So let's see what is the type. But as I said, this type is a fundamental object of the theory. So we cannot really define what's type. Like we cannot define set in set theory. So we use this notion like this is a type of or small type, or you can say it's a category of or small space. And so this is the type A. And small space we will expect the set theory problem. I mean, you know, or space or sets not form a set, right? So we don't want to meet the set theory problem. It's kind of like we fix on universe. So it's you can ignore this now, but
Okay.
yeah. It's set theory problem. Maybe we can again. So this is type 2. So this is a bigger space. So this is a relatively small space like this, but you can ignore this now. So this we got this that's a category of all space. So if there are 2 points of x, you may notice that we use this common to as a point in this space. So there are some slightly different from the common with belong, but you can basically say it's same thing. And so with this, so we can have this again the type. So this is kind of the rule of what the type is. So when give you a space, you can give and 2 points in this space, we can get the path space between this kind of same thing as the define of the high infinity. So as I said, this is not the right way to define space, define type. So what is the right way to define a type? So maybe we should use more category way to define what a type is. So any questions so far? Great. So just like the category of our topological space, there are many operators we can do between 2 spaces, like times, or so we can again to define. It's just like the space between A and B. So this are all result of the type. But I want to introduce the most general notion of construct a new type. So let's record. So this is called the sigma type and pi type. Don't worry, it's just use some fancy name, but it's something mathematicians are very familiar with it. Let's so record what is a fibration. Fibration we call a map between two spaces. Fibration is kind of like a projection. With mixing properties. So basic example is a vector bundle or fiber bundle. Yeah, or fibration. So you can think it as this is a vector bundle. This is a base space. Main fiber. The sigma type and it is used another point of view to regard this fibration. So if we denote this fiber A is so we know this map to be P is to be the pi A is point of B. So this is a space, right? This is a fiber over this point B. So we somehow define a map or a homomorphism between from the point in the base space to a space. So this can denote it as this kind of. So recall that this is the category of all space or small space. So we can define by this kind of notion. So this is, but I need to warn you that this is kind of like function. Because here we want to regard it as infinite groupoid. So this not only tell you what the fiber is, like here, what fiber is, but also tell you how this fiber twists. Since weak bundle will have some twisting between fiber, but we will see later an example of this. So if we given this kind of function, so we can define some so-called the sigma type. So we sometimes regard it as space, but sometimes regard it as space. But basically, we think it as same thing. So we denote it like this. It's just the total space E itself. So we use this kind of notion to denote the total space E. So we kind of like we gave the fiber at each point, then we glue together to get the E. And there is a notion called the type. So it's just the section. Section of P. So it's just S and P. S is B to E, and SP is identity. Right. So this This is denotes the space of the or section of this vector bundle or fiber bundle. So we denote it with some facet V. But we will see later this will have many benefits. Why we denote this like this. So okay. This is an example of this. So if the F is a constant, so all the fiber is constantly sent to a space A. So this will turn out to be A. And this I type will turn out to be B to A. As I mentioned, so you may think that okay, if I only send to a fixed point, can we only define the trivial bundle by this sigma? So as I mentioned, this may contain how the information of how fiber are twisted. So let's show example. So I will show a real define of a type. So let's take a space we are all familiar with. S1 is a circle. So we define it like this. So there is a base point in S1. Then there is a loop in the so you basically see S1 has a point, and there is a loop. So I want to stress that since all the types are defined in a formal way, so its path is not meant to consist of points. So maybe this type only have one point, but it can have this loop. But this loop, maybe there is no point on this loop. So it's kind of formal homotopy. And so maybe somehow we can we don't know what does this mean. Maybe we can somehow to denote this. So by the universal property is that if we want to find a map from S1 to A, so it's equivalent to give maybe F. It's equivalent to give FD and FL. The path space from FD to FD. Right. So this is kind of the universal property of S1. So if we want to get a morphism between a map from S1 to A, so we want to first pick a point in A, then pick a loop between S and between FB. So if we want to define a fibration, I mean, we want to regard S1 as the base of the fibration. How could we define? Let's say so we somehow need to give the fibration function from S1 to this type, right? We want to arrangement every point to a fiber. So this equivalent to C. First, we need to find the FB. Then we want to find the FL, which is a path in type of the chosen fiber. Here comes a very big problem, is that we do not know what's the path in this type. Right? Maybe we could know what's the path in a given space, but we do not know what's the path in this type. So here comes a very important axiom. It's called Univalence Axiom, which is Watsky great contribution. It says that maybe not in type, maybe in, but we for example we use type. So the path between two space in this type is exactly the isomorphism of A to B. This is the isomorphism. So somehow, because these are more like homotopy space, so this is a homotopy equivalent. So this is you can think it as space or state of the homotopy equivalent between A and B, or isomorphism in regard to the case we want to use. So this FL, in fact, we define it. It's just the isomorphism from. So IE is the automorphism of FB. So let's give our head how to define a bundle or a fibration above S1. First, we pick up a fiber. Then we found the automorphism of this fiber. So let's say a very easy example. If the FB is so-called, we want it to be R1, so we real-9. So if the FL is only the identity, so we will get the trivial bundle. But if we want to get the -1, it's i.e. it's an x into -x. What we get is a modular span. So imagine. Somehow this automorphism tell us what the fiber goes along this way.
But to me the automorphism depends on the fiber.
Yeah, this fiber. I mean, this fiber is R1 to R1 to R1.
But if it's -1, all fibers is going to be a trivial bundle anyway.
No,
It's only on the stuff. Ah, okay.
it turn around. I mean, turn.
Ah, yeah, okay. It's only on the. All right.
Yeah.
Okay.
So like we turn around the group together.
Okay.
So this is very interesting example. So that's why I mentioned that this F do not only contain what fiber it is, but also contain information how the fiber is twisted. This is just the information of the transform function. All right. So let's summarize a little bit of what what we get is that from this point of view, the type can be regarded as some big classified space. So we use this. This is a fibration about B, but I need to mention that only restriction is that the fiber is small space. So exactly function of B to this type. So that's why I kept this here. We can compare this. Maybe we can find a space version. Maybe when this is a real space, maybe there is function of infinity good point. So there is high infinity. This is pi infinity x, and maybe there is somehow we can define a infinity good point of homotopy topologic class, or maybe some good category. So we can compare. So this is maybe it's an upgrade version of this. So with this kind of very simple type. So let me talk about a little bit more why this is called univalence. And we see that in fact every fiber here is P. So it's come from a classified map from B to type. So there should be a univalence bundle, which define very easy. It just we just pick on the type, and its fiber is T itself. So this is just a pullback of this univalence bundle. Why is it called univalence? Because there are only small space. I mean, this are only small space. So there are we only classify the small vibration between A to B. So this only classify the small vibration. So we cannot call it universal, but we can call it univalence. So this is what the univalence name comes. So, but you can think it as a definition by basically captured by this axiom. So any questions so far?
So can you construct the sigma type associated to the sigma type of the types and iterate this construction?
Hmm?
Can you construct a sigma type by iterating this construction of the universal vibration, I guess?
So this it's just the B FB means this.
Okay, but then I mean this universal bundle.
Yeah.
It's a type.
Yeah.
Itself.
Yeah.
So you can also define the sigma type associated.
Yeah. But it's kind of a big type. Yeah. There is type 2, as I mentioned. There is a bigger type, a bigger universe of this.
So you do infinity types.
Yeah. Yeah, but for then use the small Yes, it's very, very elegant. So I mean, you can think that, so this is just the fiber is state, but when it comes to here, the fiber is space is type. So maybe I can talk about a little bit about the univalence mass. I mean, why we come to this idea? Maybe so called, we can also call it higher mass, which is Lewis' word. So it says that if there is a mass object, some mass object, there is category. Maybe like some vector space. We used to only classify this as up to isomorphism. But in fact, as we said before, up to isomorphism, we just only take its pi 0 to this. Maybe we can call it structure. So we only search for the pi 0. So we lose a lot of information. But like here, if we can define somehow, define a path of this structure, so this can be regarded as a type. So we are getting much more information from this. Like we can consider the pi 1 of this, or pi 2, pi 0, pi 0. But I mean, this is all very concrete. Like by this, we can very naturally to define the classified space. Like so, if there is pi 0, type. So this is an isomorphic class of space. But if we want to fix the fiber, so this is real fix the fiber. Maybe we want the fiber only to be the R. So this maybe have to factor through. There is a pullback. So this is, you can imagine it. So this is something, a group point. The point is Rn, and we also need to capture its path or path space. So its path is the automorphism of R. Just take or right click. The path is so we can define the classified space very naturally by we just take a pullback along this one point in here. Right. So another example is that if we only consider f equal to f, it's just a proposition. We only regard it properly. It's quite boring. Like f is still over k. So maybe if we classify it will be some polynomial. and idea of F, but you will have some condition. So if we only classify the category, I mean, this is the category of fields over K. We only classify up to isomorphism. We only get this kind of information. But if we notice that it's path, so the path, as we said, the path between F and F is exactly homomorphism group, okay, which is a Galois group. So this is the second hit of you to consider the path between a structure like here. So yeah, so somehow we can very naturally to regard the fields above the K into a type, and with or very natural adult construction without fundamental group, or this will be very natural by this kind of axiom. All right. I think this is what I want to see. So,
Okay, thank you very much. Are there any questions? You can also ask on Zoom on the chat. Or,
So you said that if we only classify up to pi 0, essentially we lose information.
yeah.
Is that the case, for example, in your example with vector spaces?
Yes. Yeah, if you want to.
Do we have non-trivial pi 1, pi 2?
Of course, yeah,
Okay.
that's the very, like vector space. If we only consider up to pi 0, we only get the dimension. One. But if we want to consider about maybe the path between some vector space, so this path is exactly the GL. So this is a path space, but maybe we somehow like we want to define some pi 1. So maybe is this GLN up to some homotopy of it. So maybe the homotopy, yeah. But you can believe there is right way to define this homotopy by its elementary metric. So if two metric can be treated to by this elementary metric, you can believe they are homotopy. So maybe you can believe that. So somehow the pi 1 of the vector space is like this. So this is exactly the pi 1 group. And then we can define pi 2. Pi 2, so maybe somehow we want to find the homotopy of this elementary metric. So this is pi 2. So also this we call K0, K1, and K2. But really querying can define a Kn really by some pi n Kn of some category. By some construction of some space. Maybe use QK. I mean this is real mathematician do last century.
Okay, thank you.
Any other questions? People on Zoom, please don't hesitate to write or just talk in your microphone to ask questions.
Mostly I want to introduce this kind of idea that we not only to classify up to isomorphism, but we should focus on the isomorphism, because the isomorphism even between one object has its own structure, like Galois group. Yeah, this is very important idea. But this will somehow related to the second part of my talk is that maybe we can denote it as equality. So in the further future, we will denote the path space as equality. But why we do that? Now you can feel like there are reasons because it can be defined like the isomorphism. So this is our second part of the talk. So this part, mostly I want to, show you how homotopy plays the role here.
I have a question. In the abstract, there is something you mentioned the proposition as types in logic. Could you?
Yeah. This will be in next part, next week.
Oh, next week. Okay.
Yeah. But this part I want to convince you. Even you only do mathematicians, do homotopy, your homotopy type is worth to know. And the second part I will talk about a very important thing called the proposition. This will be really benefit to every mathematician. But we will see it next week.
Okay. Still no other questions? Okay, well, if not, let's thank you again. So we'll meet again, same time, same place, same link next week.